Hi, this lesson is about the definition of the derivative and rates of change. But first, let's remind ourselves about functional notation. Remember, this expression is read as f of x, which means that f is a function of x. And y and f of x are interchangeable. So if I said y equals a linear equation like 3x plus 5, I could also write that as f of x equals 3x plus 5, where x is your independent variable and y, or f of x, is dependent on what x is. So here's an example. I have f of x is equal to 2x squared minus 5x. That's a quadratic function, and I'm going to evaluate f of a and f of a plus h. So instead of substituting in numbers the way you've probably practiced many times, this time we're going to be substituting a variable and a sum of two variables. So f of a is very straightforward. You just replace all of your x's with a. So f of a is 2a squared minus f of a. Can't do anything else with that because 2a squared and 5a are not like terms. Now let's look at what happens when I substitute f of a plus h. So that means everywhere there's an x, which is in two places, you replace that with a plus h. And so you end up with this expression, 2 times a plus h squared minus 5 times a plus h. But you can expand these. So a plus h squared, you FOIL that out and distribute the 2. So you get this expression, 2a squared plus 4ah plus 2h squared, and then distribute the negative 5. So we get this minus 5a minus 5h. Again, none of those terms are like terms, so you cannot do anything else with that expression. So again, using functional notation, we can define something called a difference quotient. And a difference quotient is basically a slope. And if you remember what slope is, your slope is your change in y over the change in x. We're just going to be using slightly different notation. So if I let one point be a f of a, and the second point q be a plus h f of a plus h, then the slope between P and Q would be the change in y, which with this notation would be f of a plus h minus f of a, over the change in x would be a plus h minus a. But the denominator simplifies to just h, so this expression, f of a plus h minus f of a over h, is called the difference quotient of the function. Similarly, this would be just another term, and it would be computed in the same way. If I wanted to know the average rate of change from a to a plus h, I would also compute that with the difference quotient. It's basically a slope calculation, rise over run. Okay, so let's find the average rate of change from x equal to 1 to x equal to 4 of this quadratic function g of x equal to 2x squared minus 1. So remember, change in y means that's when you're substituting in the x values in for the function. So you always are subtracting the y values, in this case the g of x values, and in the denominator you should be subtracting the x values. So I have to evaluate g of 4 and g of 1 and subtract them. And in the denominator you're subtracting the x values, so I have 4 minus 1. When you plug in 4, remember you're substituting g of 4. That means you're plugging it in here. So 4 squared, that gives you 16 times 2. That's 32. Subtract 1. That's where 31 comes from. When you plug in 1, you get 1. So when you simplify, you get 30 over 3, which means the average rate of change for that function from 1 to 4 is 10 units. Okay, it's just a slope calculation. All right, so that leads us to the derivative. So the derivative is really where we spend most of our time studying what the derivative is and figuring out how to compute it, what it represents, how to graph them, etc., throughout most of a Calculus 1 course. And so here is the definition of the derivative. The notation, or one of the notations, is what you see here. This is read as f prime of x, and it means the derivative of x. And so the definition is basically it's your difference quotient as you take the limit as h approaches 0. So what that means is that you're computing the slope between 2 points, but those 2 points are getting very close to each other. So close that they actually become one single point. So it is your difference quotient with the limit as h approaches 0 before it. So let's understand this definition a bit more. So again, recall that f of x plus h minus f of x over h is what we call the difference quotient. And remember that the derivative is going to represent the slope, but because it will be a single point, because as h approaches 0, it won't be an average rate of change, it will be an instantaneous rate of change. So it represents the slope of the tangent line to a curve, a single point. So here, if I explain this graphically, if I wanted to know what the slope is on the curve from a to a plus h, well, a is this blue line that you see here, and a plus h is this other point here. If I wanted to know the slope of the line between these 2 points, that would actually be a secant line, because it would intersect the graph at 2 points. And I would compute that by just taking my difference quotient. But as h approaches 0, this gets closer to a, and so my tangent line actually becomes, my secant line actually becomes a tangent line, which is this one that you see here in blue, and that derivative represents the slope. So the slope will be the difference between these, the f of a plus h minus f of a over h as h approaches 0. So that part is really important, because your 2 points cannot be far apart. They have to be approaching closer and closer to each other. Okay, so memorizing that definition is important, the one in the box above, and being able to use functional notation in order to compute a derivative will be important. So here are different ways that you may be asked to find the derivative. So you might be asked to differentiate f of x. That means find the derivative. You might be asked to find the slope of a tangent line to a curve at f of x. Remember, the slope of a tangent line is the derivative. You might this vocabulary might be used. You might be asked to find the instantaneous rate of change of one variable with respect to another. Again, instantaneous means at a single point or at a single moment of time, depending on the problem, which again goes back to a tangent line, not an average rate of change like a secant line. More specifically, you might be asked to find the instantaneous velocity of an object at a particular point in time. Again, that represents a single point, not an average of 2 points or a time range. And you might also be asked to find the acceleration of an object. So the acceleration is also a derivative, because acceleration is the derivative of velocity. So we'll be practicing all of those in either this lesson or future lessons. Okay, so here's a bunch of notation, and these notations really depended on which mathematicians were coming up with this. There was Newton and Euler and Lagrange all coming up with different concepts regarding derivatives, and they use different notations. So y prime represents a derivative just like f prime did above. It may also be written like this, dy over dx. This should kind of remind you of change in y over change in x, and that's because they are related. So dy over dx represents a derivative. Df over dx also represents a derivative. Remember, you can say that f of x is y, so it's just like an interchanging of that notation. It could also be written like this. This is the derivative of f of x with respect to x. It's just a different way of writing the previous one. These two are almost the same. And then capital D f of x, this means the derivative of f of x. And here it's getting more specific. It's the derivative of f of x with respect to x. So it's letting you know that you are taking the derivative with respect to x, just like these tell you that it's with respect to x. So notice that dy over dx and df over dx are written as ratios. And so that's just emphasizing that you're taking the derivative of a function that you call y or f of x with respect to x. And later on in the course, we'll discuss this ratio independently. These are called differentials. Dy and dx are considered to be differentials, and that'll be important later in the course. Okay, so it is possible to take higher order derivatives. So remember, f prime means the first derivative, just like all of this notation means the first derivative. But you can take a second, third, fourth derivative. So this is the second derivative, also read as f double prime. And these are other variations of the notation above. And then we have f triple prime, which could also be written with this other notation. And anything other than the third derivative would have a little number in the upper right-hand corner. So this is the nth derivative of f. So if it's the fourth or fifth derivative, you would just put the appropriate number there. And so that's the different notations, and we flip-flop between different types of notations. So we want to find the first four derivatives of this function. So for now, we're just going to be using the definition to do that. And the definition, remember, is the one up here in this box. So that'll be important for you to always keep in mind. Whenever you're asked to find the derivative by using a definition, this is the definition. We'll be learning shortcuts or rules later on in the course. So we need to distinguish between the different ways to find the derivative. So here I didn't exactly show all the work to do that, but I wanted to show you what happens as I take the first, second, third, and fourth derivative of this third degree polynomial. So when I take the first derivative, my third degree polynomial becomes a quadratic, a second degree polynomial. And my second degree polynomial, when I take the derivative, I get a linear function. And when I take the derivative of the second to get the third derivative, I get constant. And then the derivative of the constant is 0. So then anything other beyond 4 in this example would still be 0. So you'll learn soon that the derivative of 0 is just 0. So when you have polynomials, as you take derivatives, the function gets simpler in terms of degrees. And that will be true always with polynomials. Not the same with radicals or rationals or trig functions, but with polynomials that will also be the case. So here we have linearity rules of the derivative. What this says is that if you're taking the derivative of the sum of two functions, you get the same result if you take the derivative of each function individually and then sum them. The same is true for the difference. And the third one, assuming c is a constant, is saying that if you're taking the derivative of a constant times a function, it's the same as taking the derivative of the function and then multiplying it by c. So that might make things a little easier in some cases. So linearity rules cannot be applied to the product of two functions or the quotient of two functions. So there'll be a specific way to handle derivatives when you have a product or a quotient, which you will learn soon. Okay, so we have displacement, velocity, and also acceleration, which we'll talk about soon. So if we let s of t be the displacement or the position of an object moving in a straight line, sometimes you might hear the term rectilinear line, which means straight line. S of t would be the position function. And if we want to determine what the average velocity is from t equal to t equal to a plus h, so in other words, a time interval, some time has elapsed, that is again just a slope calculation. This is the change in y over the change in t. And remember, when you subtract a plus h minus a, well, the a's cancel, which is why we just have an h in the denominator. That's again what we called the difference quotient just a few minutes ago. When we want to know the instantaneous velocity, well, that's when h approaches zero, meaning this time lapse becomes a single moment in time. As h approaches zero, t equal to a and t equal to a plus h are actually the same time. And that's, again, a derivative. So if I take my difference quotient and I apply it to the definition of the derivative, so instead of f of x plus h, we're going to have s of t plus h minus s of t over h, and we're taking the limit as h approaches zero. So the derivative of your displacement or position function is your velocity function, and the definition of instantaneous velocity is what you see here circled. And again, from a graphical perspective, the instantaneous velocity is computed the same way you would compute the slope of a tangent line at a curve at a particular point. Similarly, we have instantaneous acceleration. Instantaneous acceleration would be the second derivative of displacement, and the second derivative of displacement is the first derivative of velocity, which we call a of t for acceleration. Instantaneous acceleration because it's again at a single moment of time. So here's your difference quotient with respect to v. You take the limit as h approaches zero, and so the second derivative of displacement is your acceleration function. This can go on, just like as I mentioned, you can take either a third derivative and a fourth derivative. So if you took the derivative of acceleration, that's called the jerk, the jolt, or the surge of a function. We don't really spend any time on that concept in this course, but it may come up in other courses like physics. All right, so here's an example. We want to find the velocity and the acceleration at t equal to 2 seconds for an object with a displacement function of s of t equal to 2t squared plus 3t minus 1. All right, so I need to compute my velocity at a single moment of time at 2 seconds, which means I need to compute a derivative. Remember that your velocity function is the derivative of the displacement. So I have to apply my definition, which is again this right here. You have to use the notation s of t plus h minus s of t over h. So here's the s of t plus h minus s of t part, and then here's the over h. That will always be the same in these problems. But s of t plus h, that just means that all of your t's get replaced with t plus h. So that's what you see here. And then minus s of t, well, that's what you see here, and you need parentheses because you have to distribute that negative. Then the rest of it is just a lot of algebra, expanding and combining like terms. So on this line, I FOILed and distributed the 2, and I also distributed the 3 here, and I distributed this negative across the trinomial. So that's everything you see on line 2. And then from line 2 to line 3, I combined like terms. So the 2t squareds, well, they cancel. The 3t's, they cancel. The 1's cancel. And I'm left with 4th plus 2h squared plus 3h over h. Now remember, this is a limit. I can't just apply direct substitution here or even here, because if I do, my denominator will be 0. That's a problem. Same thing here. But I can simplify further because my numerator has a common factor of h. So I factored out an h, leaving me with h times 4t plus 2h plus 3 over h, but that allows us to cancel the h's, the one on the outside and the one in the denominator, and that leaves me with this line. And now I can apply direct substitution, and when I plug in h equal to 0, that middle term cancels, and you're left with a general velocity function of 4t plus 3. Okay, so if I just wanted to know what the general velocity function is, it's 4t plus 3, but we were asked to evaluate it at 2. So now we have to take the 4t plus 3 and plug in 2. So that's what you see here. The velocity at 2 is 4 times 2 plus 3, that's 11. And the units were in meters per second. So the velocity is 11 meters per second. Okay, so if we go back, we've answered the question, but I have another part here to show you how to compute the acceleration. If I wanted to know what the acceleration is at 2 seconds, that means that I need to compute the derivative of the velocity. Remember, that's true by definition. So that means I'm going to apply the definition of the derivative to this function. So I have v of t plus h minus v of t. This is the v of t plus h part. This is the v of t part, all over h. And just like the previous example, there is some distributing and simplifying you can do. So when you distribute, you get this line here. Then the 4t's cancel, the 3's cancel. I'm left with 4h over h. The h's cancel. So I get a constant of 4, which means you don't need to plug in the 2. It's just a constant acceleration. So you have a constant acceleration of 4 meters per second squared. Okay, so that's it for this lesson. Give the homework a try. Good luck.